Hello, this is the video lecture on hydraulic machines under CE 202. I am Professor Virukon from the Department of Civil Engineering. So far, you have learned several sections under CE 202. Especially, you have covered applications of conservation laws, dimensional analysis, and flow in pipes. And the knowledge that you have gained from those sections is very important to follow this course on hydraulic machine. We have 3 hours in the schedule to cover the section on hydraulic machines. As you can see there, we will be studying positive displacement machines, rotodynamic machines, and their characteristics during these 3 hours. This shows the learning objectives of this hydraulic machine section. After completing this section on hydraulic machines, you should be able to analyze flow through different hydraulic machines, especially turbines and pumps. And also you should be able to select a hydraulic machine for a given application based on the performance characteristics of hydraulic machines. And I have uploaded several course materials under this topic. You can find lecture notes and also these PowerPoint slides, and those are very useful for you to follow this lecture. So I expect you to have read and gone through those before listening to this video. And also I will upload tutorials and answers, and also you are expected to refer recommended textbooks and other open educational resources or OER to enhance your knowledge on hydraulic machines. And what do you understand by a hydraulic machine? It is a device used to convert mechanical energy to fluid energy or vice versa. Do you have a hydraulic machine in your body? Yes or no? Yes. Your heart is a hydraulic machine. Is a hydraulic machine. Now the essential feature of a hydraulic machine is that there must be an inflow and outflow of fluid, and there is a shaft work output or input to the machine as shown in this diagram here. You can see inflow or outflow here, and there is a shaft work output from the hydraulic machine. And there are two types of hydraulic machines that we use in industry. In one type we call pumps, mechanical energy is converted to fluid energy. On the other hand, in turbines, it is vice versa. Fluid energy is converted to mechanical energy. Now, if you see this slide, next slide, see what happens in within a hydraulic machine. So, energy that is contained in the fluid is changed while the fluid passes through the hydraulic machine. You have learnt about energy contained in the fluid, and you know energy can be in different forms. The mechanical energy in a fluid can be there as pressure energy, and then kinetic energy and potential energy. And you also have learned that energy per unit weight of fluid can be expressed as head of fluid. Head. The head has the units of length, and therefore we have total head as pressure head plus velocity head plus elevation head. I am sure you have used this total head under pipe flow section that you have already learnt, or in the applications of conservation laws that you have learnt during previous lectures. Now, when it comes to hydraulic machines, so we have two types, pumps and turbines. Now, if you have this hydraulic machine and there is an inlet and there is an outlet, at the inlet, yes, we can measure pressure and we can also measure velocity and we can also measure the elevation. Therefore, total head at the inlet can be expressed as this one, pressure head, Ps over gamma, gamma is rho g, plus V squared over 2g plus Zs at this place. Then similarly, the total head at the outlet or delivery in this case is given here. So difference in these two is called the head of the machine. Now when it comes to a pump, so pump head can therefore be written as head at the outlet minus head at the inlet. Then head, turbine head, head at the inlet minus head at the outlet, because energy is extracted in the turbine. So head at the inlet is greater than the head at the outlet. Now let us see the use of hydraulic machines in industrial purposes. The application of hydraulic machines is not new. This shows a water wheel or Chinese noria. According to the recorded documents, this noria had been used as early as 3rd century BC in China for irrigation purposes. You can see this wheel is rotated due to the water flow, and water is lifted and dumped to this canal and is conveyed to irrigation fields. And similarly, we have evidence of use of water wheels like this to harness mechanical energy. Say this rotates due to the flow and a torque is generated in this axle or the shaft, and that mechanical energy is used inside this factory. And similarly, the Archimedes screw had been used to pump water for irrigation purposes. See, here is the water source, maybe a river, and then by rotating this screw, water can be lifted to a high elevation for the purpose of irrigation delivery. And, uh, and this is the modern Archimedes screw. It is the same thing as you can see. These are still in use and are still useful. You can see the concepts of water wheels, and what is shown here is called undershot wheel, and this is called overshot wheel. You can see water power is generated by these wheels. And here also the axis of these wheels can be horizontal or vertical, as you may require in the applications in the industry. So water flows under certain head, so there is some energy here, and that energy is converted to mechanical energy by this arrangement. So these are like turbines. So mechanical energy is harnessed through the shaft. This also shows the water power uses in early days. Now this shows sawing of timber. So there is the water wheel, and you can see sawing timber. And this shows a grinding wheel or grinding mill, and this is the water wheel, and this horizontal axis, as you can see, conveys the energy required to grind the wheat by this mill. And here what you can see is harnessing of water by this vertical shaft, and energy is transferred by mechanical means through belts and shafts, and finally the energy is used for textile industry. Even today, in some parts, in some of these tea factories in Sri Lanka, you can see some ruins of this type of mechanical energy transfer systems where water has been used to generate power, and then mechanical systems, belts and shafts had been used for tea industry. Now, this slide shows about the classification of hydraulic machines. So hydraulic machines are broadly classified into two types. One is called positive displacement type hydraulic machines. The other is called rotodynamic type hydraulic machines. Now okay, let us see the difference between positive displacement machines and rotodynamic machines. In a positive displacement machine, fluid pressure is changed by changing the active volume inside the machine. Okay, change in the active volume inside the machine. Now this figure shows you a positive displacement type machine. What happens here? There is a piston. The active volume of the machine is here. you can see the active volume inside the machine is changed by the movement of this piston. Low pressure fluid is sucked in and then pressurized and is pumped out. So there are many examples for this type. Reciprocating pumps, check pumps normally operated by hand, and vane pumps, rotary pumps, diaphragm pumps, and so on. We will see these very soon. Now, what is the difference between rotodynamic machines and positive displacement machines? In rotodynamic machines, the energy is transferred to fluid by torque rotation. The active volume inside the machine remains same. Unlike here, the active volume inside the machine remains the same. The best example is here, the centrifugal pump. In many domestic water pumping, you may have seen the use of centrifugal pumps. In those, as shown here, the active volume inside the machine remains same. Fluid moves in here and goes out from here. The active volume inside the machine remains the same. So I'm sure you know the difference between these two types now. Okay, so this is heart. This is the heart. So you can see the active volume inside these compartments change. Active volumes inside these compartments change. So we can classify heart as a special type of positive displacement machine. Okay, positive displacement pumps apply pressure directly to the liquid by a reciprocating piston or by a rotating member in the machine. And these positive displacement machines can be classified into two types. One is reciprocating type positive displacement pumps. The other is the rotary type positive displacement pumps. In all these, the active volume of the fluid is changed at each cycle. Fluid is forced by changing the active volume inside the pump. And these positive displacement pumps are very much used for high pressure applications in industry, in hydraulic power transmission, etc., as you will learn in other lessons of this program. Okay, this slide shows the classification of positive displacement pumps here. So there are reciprocating pumps and rotary pumps, and there are different types of reciprocating pumps, piston pumps, diaphragm pumps, and so forth. And also there are different types of rotary pumps. In these, there is a rotating element. There are gear pumps, lobes pumps, screw pumps, etc. We will see them in next slides in detail. Now, these are piston pumps and diaphragm pumps, reciprocating type positive displacement pumps. Here you can see what we call a double acting reciprocating pump. You can see a cylinder here and a piston rod is here. So by the reciprocal motion of this piston, you can arrange to suck fluid and pump fluid. That is to increase the pressure and energy of the fluid. This is double acting because this side and this side form two compartments, and when one is a suction stroke, the other side is a delivery stroke. Okay, you can see clearly how it works by changing the valves here, suction valves and delivery valves. And this is also a simple demonstration of positive displacement pump. And here again, a piston pump you can see used in automobiles, bent axis piston pump. So this disc you can see is inclined and these pistons are coupled to this disc. So when this rotates, you can see the volume is changed, thereby fluid is pressurized. Right. Here is another one. It's called diaphragm pump. So this is the flexible diaphragm, which is in yellow color, and this is the reciprocating arm. You can see fluid is sucked in and is pumped out during a cycle. They are examples of reciprocating pumps. Okay, let us see a few examples of rotary type positive displacement pumps. This is a gear pump, very much used for high pressure applications in automobiles. And shows also a gear pump. You can see green color shows the low pressure inlet side and red color areas show the pressurized flow leaving the gear pump. And this slide also shows us few more rotary type positive displacement machines. This is a lobe pump, two lobe rotary pump. So these are the two axes about which these lobes are rotated. And this is a vane pump. You can see the low pressure zone is shown by this blue color, and red color zones show the high pressure side. And inlet and outlet are at these places. And this shows a screw pump. This is the inlet and this is the outlet of pressurized flow. The screw is driven by a motor fixed to one of these sides. So let us see the other type, the rotodynamic machines. There, energy is transmitted to fluid by torque rotation. Active volume inside the machine remains same as we discussed before. These rotodynamic machines essentially consist of a rotating element inside it and is known as impeller or runner. And this impeller or runner has vanes or blades. So it is a disc with number of blades in it. So in a rotodynamic pump, for example, the impeller does work on the fluid, like in the centrifugal pump you have at home. Impeller imparts or give some energy to the fluid. Energy contained in the fluid is raised by the pump. So you can lift water to a high elevation. In a rotodynamic turbine, it is the other way. The fluid does work on the runner. For example, Pelton wheel that you have seen maybe in your schools or during your field visits, you may have seen them. Water impinges on series of buckets and the runner rotates and generates torque, which is used to drive either a generator, and finally you can convert mechanical energy to electrical energy, like in many of the power stations we have in our country. Now this is again about rotodynamic machines. From now on, we focus only on rotodynamic machines in this course. As I told, there is an essentially a runner or impeller inside the machine. It is the rotating element and it has blades. Now this is an impeller of a centrifugal pump. The small pumps that you have at home, like domestic water pumps, usually have this type of impellers. So you can see there are blades. This is covered impeller. There is a plate this side and that side. Inside you can see blades. We call blades or vanes are like this. You can see the edge of those here and the beginning part is here. So what happens is fluid enters here, water enters here and leaves here with high energy, usually high pressure. Right. So this is the rotating element inside a rotodynamic centrifugal pump. And it is like this. This is the shaft and this is the impeller shown here, is here. And this is driven by the electric motor. So you can see water enters from here and is delivered through this, which comes out from this periphery of the impeller, is collected and pushed through this delivery of the pump. Delivery flange is here, is connected to a pipe. And here is an impeller or runner of a turbine, Pelton wheel turbine. And here is the axis, you can see, and these are the vanes or we call buckets connected to the impeller. So this is the impeller. Altogether is the impeller. So fluid is arranged to come through this nozzle and this water jet comes out from the nozzle, impinges on these buckets. So this impeller rotates and a torque is generated and coupled here to an electric generator to find some finally to generate electricity in the case of hydropower turbine. So this is the impeller or runner of a turbine, one type of turbines, and this is an impeller of one type of the rotodynamic pumps called centrifugal pumps. Right? It is like this. Now these rotodynamic pumps are also classified into two types. They are called impulse type and reaction type. So let us see the difference between these impulse type rotodynamic machines and reaction type rotodynamic machines. Impulse type machines, in an impulse type machine, the kinetic energy of the fluid is converted to mechanical energy. They are usually the turbines. And here you can see a turbine. This is an impulse turbine. Best example is the Pelton wheel turbine. Now here is the reservoir, or water is at a high elevation, and water is brought down to a low elevation here through a penstock, usually a steel pipe, and there is a nozzle here. So total head or the energy per unit weight of fluid is here is potential energy. And when this water is brought to this level, energy is converted to kinetic energy. So the velocity at this nozzle, which has a small opening, is very high. So there is a lot of kinetic energy contained by the fluid. So a jet is formed and this jet impinges on these buckets. So this rotates about the horizontal axis in this case, and a torque is generated. So this type of machines are called impulse machines, where the kinetic energy of the fluid is converted to mechanical energy. So best example is Pelton wheel turbine. They usually operate under atmospheric pressure. So water jet impinges here and pours down. Then what is the other type? Is the reaction type. In a reaction machine, pressure energy and kinetic energy of the fluid are changed while passing through the impeller. So best example is centrifugal pump, like here. So when we take a section across here, you have a section like this. So this is the impeller, and fluid enters through this center and leaves through this part. Now here, fluid fills this passage, and fluid is under pressure. It is not under atmospheric pressure like in impulse machine. Pressure is under pressure is larger than the atmospheric pressure here. Pressure increases from center to the periphery when water moves through the impeller. So difference between the two types is that in reaction machines, pressure energy and kinetic energy of the fluid are changed as it moves across the turbine. And there is an essential component here, like the nozzle in impulse turbine. There is an essential component here, that is the spiral casing or volute casing. Volute casing is a curved shaped device, and it has increasing cross-sectional area like this. In the case of a pump, flow passes through the volute like this, and the velocity of the fluid reduces because you can see the cross section is increasing here. Impeller rotates this way. Fluid is thrown out from the impeller at a very high velocity. These impellers rotate at a high velocity. For example, maybe 1500 revolutions per minute or 3000 revolutions per minute, depending on the design. So the velocity of the fluid here, which is leaving the impeller, is very high. Is very much greater than the velocity that is required in the pipe. So there is a lot of kinetic energy contained in this fluid, and that is recovered as pressure energy as it moves along this volute casing. In the case of a turbine, it is opposite. Fluid enters from here and pass through volute casing and through the impeller and leaves the impeller at this place. I hope you understood the difference between reaction machine and impulse machine. Okay, when it comes to the classification of hydraulic machines further, we can classify reaction machines to another three types: radial flow type reaction machines, axial flow type reaction machines, and mixed flow type reaction machines. And impulse machines have no more classification. Now let us see the difference between these three types of reaction flow machines. Now when it comes to pumps, the rotodynamic pumps can be classified again into radial flow pumps, axial flow pumps, or mixed flow pumps. This centrifugal pump is the best example for radial flow pump. And axial flow pumps are available and you may have seen them as well. See this slide carefully. This first figure shows a radial flow type pump, impeller of a radial flow type pump, like centrifugal pump impeller. Now here you can see the inlet is here, and this is the shaft which is coupled to drive the impeller. Fluid is sucked in and is sent out at high pressure by this rotating impeller. Now in this type, flow is radial inside the impeller. Relative to the impeller, if you consider the motion of fluid, it is radial. And a fluid particle remains almost in one plane perpendicular to the direction of rotation. So the axis of rotation is here, plane perpendicular to it is here. So once it enters here, you can see, so it moves through the impeller but remains in this plane. If you consider flow relative to the impeller, flow is radial. Otherwise, it is spiral. Now here, is the radial flow type impeller. And this is an example of axial flow type impeller. We call it propeller. Now what is here is the impeller, and it has blades. One blade is here, another blade is here. This is the axis of rotation. This is coupled to a motor. Now fluid enters here and leaves the impeller here. You see the flow is axial. Here the flow is departed at almost 90 degrees. Comes here and leaves there. But here it is in line. Inlet and outlet are in line. And fluid remains on a cylindrical surface. If you see here, a fluid particle that enters here remains at the same distance from the axis of rotation. This is the axis of rotation. So fluid particles move like this, takes spiral path, but remains almost at same distance from the axis of rotation. It is different from this radial flow type, where flow remains in a plane perpendicular to the axis of rotation and flow is radial relative to the impeller. But here, see, it's like spiral flow. So this is the basic difference between axial flow type and radial flow type impellers. Then mixed flow type is in between these. So we have different designs, as I mentioned, to improve the efficiency of the machine. So sometimes you have complex designs where flow inside the machine or impeller is not radial or not impeller, but is a complex combination of radial and axial flows. So their flow pattern depends on the design. So they are called mixed flow type impellers. So most of the modern turbines are of this type of mixed flow type turbines in order to harness the energy at maximum efficiency. So there are reaction type turbines and reaction type pumps. So we will see those in detail now. Now this is the simple case that you are familiar with, the centrifugal pump. So here is the inflow, here is the impeller, direction of rotation, and the outlet. Okay, so it's a radial flow machine. Now here, this is the pump and this is the motor is coupled. The shaft is here, the shaft is coupled to the motor. So you have the driving mechanism here. So inflow is from here, outflow is from there. Now the impellers can be of different types. These all are radial flow type impellers. So one common type of impellers used in domestic water pumps is here. They are called closed impellers. You can see more details in the printed notes as well. Closed impellers. These are called open impellers. This is one side open. These are sometimes called shrouded impellers. So they have different usages. If the fluid that you want to pump have debris or impurities, so you use this what we call clogless or open impellers. Because if there are impurities, debris, sand, or some material, see, there is a possibility of clogging inside or blocking inside this impeller. So in those, say like sewage pumps or pumps used in mines, etc., where slurry is pumped, you have these open impellers. Whereas for clean water pumping, like domestic water pumps or water supply schemes, you may have this type. So sometimes in large applications, large pumps, you do not have this type, you have open type impellers. See, this is the impeller and the volute casing. I'm sure now you are very familiar with the setup of radial flow type hydraulic machine. Right. This is axial flow type pump. So this is the impeller, and here you can see a picture, and this is the impeller. See, the impeller blades are like our fans, blades in our fans. Table fan, now you have similar axial flow pump. It's an axial flow pump. Only thing is it has no cover like this. So here this is driven by a shaft and fluid enters here and leaves through this. Enters here and leaves through this. And this type of axial flow pumps are very much used in water supply intakes. They are more efficient than centrifugal pumps or radial flow type pumps for low head applications. That means you use them for pumping larger volumes to lower elevations. So you lift water from here, say to a water treatment plant. So if you have seen the water treatment plant next to Akbar Hall, you see the Mahabel River is there, and there is a intake, and inside the intake you have this type of installation of axial flow pumps to lift water from river to the treatment plant. Whereas from treatment plant to the storage tanks that we have, for example, one near Ivogen Inksol, you see the elevation difference is very high. We use centrifugal pumps because they become more efficient than axial flow pumps for high head applications. Now, this pump or the impeller rotates at about 3000 rpm. So you see all that water that you get for your use inside the faculty or inside the walls comes through the blades of these pumps. So this is a complex operation. Now you can see, right? And there are sometimes installation like this. So your pump is here. This is the shaft. This is the what we call axial flow. Sometimes we call this propeller pump. So water level can be here up to here and is pumped through the pipe here. Okay, these are axial flow impellers. So you can see all these in our laboratory. We have axial flow pump impellers. We have kept them open for you to see, and we also have centrifugal pump impellers. You can come and see them. The pumps are only one types. Then we have turbines, where the fluid energy is extracted from the fluid. Especially, we have water turbines, where energy contained in water is converted to mechanical energy and then to electrical energy in hydropower stations. In Sri Lanka, we have many hydropower stations and we have different types of turbines, radial flow type turbines, axial flow type turbines, and mixed flow type turbines. They are all rotodynamic type. We also have impulse turbines. Like Laksapana, we have Pelton wheel turbine. They are impulse type turbines. Like Victoria or Andanigala or Kotmale power stations, you can find reaction type turbines. They are either Francis type or we call radial flow turbines or mixed flow turbines, close to radial flow but not exactly radial flow. They are mixed flow. Modern Francis turbines are mixed flow turbines and they are used to generate hydropower in our country, as you know. And same time, there are many small hydropower projects now, and in those small hydropower or mini hydropower projects, we have again all these types of turbines installed. When the height is very large, in other words, when there is a high head of water, impulse type turbines are more efficient. Therefore, you can see Pelton wheel turbines installed in some of these small hydropower plants and also in Lakshapana hydropower, major hydropower plant. But like in many small hydropower applications where the head available is not very high. For example, the number of small hydropower plants along Sudhuganga. Do you know where Sudhuganga is? It is the river that carries water from Ukuela power stations to Bovatana reservoir. It's called Sudhuganga. There are about 8 or 10 power stations and discharge is about 60 cubic meters per second but drop for the head available, elevation head available is not that high, maybe 5-6 meters at a one place. So then axial flow type turbines become more efficient and all the installations there are axial flow type turbines. We will see them soon in next slide. Now here, what is shown in this slide is a radial flow type turbine. You can see this is the spiral casing or the volute that we discussed before. See the, like in centrifugal pump, see the spiral casing and water enters through this one and flows through this and then enters while it flows around this one water enters through the runner. So this is the runner. So this is radial flow. You can see inside the runner flow is radial and water flows out from the center. In the case of a pump, you have flow in the other way, enters here and leaves through the spiral casing. Now here it is opposite, comes through and goes down. So here is the turbine. Now you can see is a mixed flow or Francis type turbine here. Oh, it is called runner. This is called runner. These are the blades. Okay. The flow is controlled by guide vanes here. Flow into these runner is controlled by the guide vane arrangement here. There is the complex control system to change the power output based on the demand. As you all know, as you all know, power, power output P equals efficiency times Q rho G H. So efficiency is here. Q is the discharge, H is the head available. And in pumping systems also you know power required to be imparted to the fluid to lift a discharge of Q to a height of H is Q rho GH, and this is the efficiency of the pump. Similarly, the power output from a turbine is the head available across the turbine, There may be reservoir here at a higher elevation and a tail raised down. Say reservoir elevation is here. The water comes into this one through a penstock and goes out. So the head available across the turbine is all this from here to there. So that is capital H, and there may be head losses inside. So that has to be deducted. And inside the machine there is efficiency and there is a flow rate. Then the power output is this. So whenever there is a fluctuation in power output, that is the demand, you cannot change H because reservoir water elevation is constant, almost constant. So you have to change either Q or rho or G. So what happens is you change Q here to meet the required power output P. So Q is changed through a feedback mechanism using these guide vanes here. Those are called guide vanes or sometimes called wicket gates in turbines. We will see more about these in next slides. Okay, this slide shows you the axial flow type reaction turbines. Now what you can see in this figure is an impeller of a Kaplan turbine. Axial flow turbines are sometimes called propeller turbines or Kaplan turbines. Now you can see the size of this one. See, there is a person here and you see the size of the impeller. Now this impeller also has blades, and what you can see here is that these blades can also be turned about the hinge on its shaft. Now these are the blades of the impeller, and there is a mechanism here through which these blades can also be turned. So this angle slope here can be adjusted to control the discharge through the machine. This is the spiral casing, and there are also wicket gates or guide vanes to control the discharge, as same as in the reaction turbine of radial flow type. So using this type of blade rotating mechanism, the efficiency of the machine can be kept at a higher level. So you can see the flow enters through the spiral casing or volute casing and then passes through the wicket gates or guide vanes and then flows through the impeller. When the flow goes through the impeller, flow is axial. You can see is axial, and then flow passes through the draft tube to the downstream. And the impeller is connected through the shaft, and the shaft is connected to a generator where the torque or the mechanical power is used to generate electric energy. What you can see here is another installation, especially in small hydropower installations. You have what we call bulb turbines. Here again, the impeller is an axial flow type impeller. Flow is arranged to pass through this impeller, and what the difference in this is that the generator is also encased here. The whole unit is submerged and only the electric cables come out from water. So these are called bulb turbines, and they are economical for small hydropower installation under certain conditions. This slide shows an actual installation of a Kaplan turbine in a mini hydropower installation at Suduganga. The head difference is shown here, which is about 8 meters between here and here. And flow is arranged to pass through this passage. And these are the guide vanes or wicket gates. And the runner diameter is 2.3 meters. This is the runner. You can see this white one here is the runner, and this is the axis. So the flow enters through the spiral casing, which is not shown clearly here, and enters into this impeller. Flow is axial when it passes through the impeller here and passes to the downstream. And shaft is connected to the generator here through a gear mechanism to generate hydroelectric power. So this type of installations are common for low head small hydropower installations in our country. Okay, what you can see here is impulse type machine, the Pelton wheel turbine. Now you can see the impeller of Pelton wheel turbine here, and there are nozzles. Water flows through the nozzle, and jet created by the nozzle impinges on these buckets. Now here is the demonstration. See, water comes through this one and nozzle is here, and the discharge through the nozzle is controlled by what is called spear valve. So it has a spear rod like this, and this can be moved this way or that way to change the opening of the nozzle. So as you know, the velocity here depends on the head available, and specifically you know that velocity is square root times 2gh into a coefficient of velocity. Then the discharge is q times the discharge is area times the velocity. So by changing the opening of the nozzle, you can control the discharge through the nozzle. Thereby you can control the power output from the turbine. And the jet impinges on these buckets and falls down, and this is under atmospheric pressure. So in this case, you see there are number of jets, 1, 2, 3, 4, 5, 6. The number of jets depends on the design, the discharge, and the impeller size. The impeller is here. And in this case, you can see there are two nozzles or two jets. Water comes through this side and comes through this and this jet. An axis is here. This axis is connected to the generator. So this is a common Pelton wheel installation. This can be vertical axis or horizontal axis. In this case, this is horizontal axis installation. We have Pelton wheel installations in Sri Lanka, like in Lakshapana hydropower station or in many small hydropower stations. Pelton wheel turbines are the most efficient when you have a very high head for your installation. Now this shows the other type of commonly used impulse turbine. They are called turbo impulse turbine. And in these, as you can see, the nozzle arranges the jet, water jet impinges on the buckets like this. It is different from Pelton wheel turbines. The jet impinges from one side and then moves to the other side. It is deflected like this. Whereas in Pelton wheel, jet impinges on the bucket perpendicularly like this. And here is the demonstration. So you can see jet comes from this side and departs the blades or the cups from this side. And these turbo impulse turbines are efficient under certain conditions. If the head is less, like see, like in certain hydropower installations, like Watabala mini hydropower installations, they use turbo impulse turbine. And in fact, you don't have to go anywhere to see these different types of turbines. If you come to the hydraulics laboratory, you can see Francis turbines, their impellers, Kaplan turbines and their impellers, or impulse turbines, either turbo impulse turbines or Pelton wheel turbines. So you can come and see them. They are there for you to see and learn more. Okay, theory of rotodynamic machines. Now you have learned the flow pattern inside different rotodynamic machines. The rotodynamic machine may be a pump or a turbine, may be radial flow type, axial flow type, or mixed flow type. What is common in all rotodynamic machines is that there is an impeller inside, and when fluid flows through the impeller, the angular momentum of the fluid is changed. So that is how the energy is exchanged between the fluid and the impeller. In other words, transfer of fluid energy to mechanical energy or mechanical energy to fluid energy. So we can apply conservation laws to derive an expression for power transfer between fluid and the mechanical component. That is the topic for the next class. But before we stop, you need to know this concept that we use to derive the power transfer. That is, at the steady state, the rate of change in angular momentum of the fluid passing through the impeller is equivalent to the torque about the axis of rotation. And you have learned this under the application of conservation laws to control volumes in previous classes, where you have applied the same concept to calculate torque in a sprinkler, for example, in irrigation sprinklers. So recall what you have learned in those classes and be ready to follow the next video. Thank you. We stop here.